when we talk about continuous probability distributions, so we have two different concepts. The thing we want to talk about is the probability density function, or the PDF, okay? Not the PDF of your document, okay? So for a continuous distribution, we have a range. So the interval between A and B, let's say, where the probability is defined. And for every value in this range, every value of x in this range, we have a probability density defined, right? So the probability density functions gives you the probability for every value of x. Okay, is that clear? So whereas for a discrete distribution, this probability is only defined for some specific values of x. Okay, so that is the main difference. Okay. So the immediate question that you might want to think about is, for a normal probability, we know that when you add up the probabilities, it all has to add up to 1. Yeah? So now, what is the corresponding analog of that in the continuous distribution? Okay? So that has to be the area under the curve. Okay? Okay, so the corresponding condition for a continuous distribution is that, so typically for a univariate distribution, so that means you only have a single variable like x, the range is going to be, the maximal range possible, because this is real value, it is going to be between minus infinity and plus infinity. Okay? So hence, for that, the corresponding area under the curve is going to be given by this definite integral, right? Okay? So I hope you can remember what the integration does. The integration simply gives you the area under the curve, okay? So while for discrete distributions, we talk about summation, for continuous distributions, we typically will replace all the summations with the corresponding integrations, okay? In a sense, that is the only difference between a continuous distribution and a discrete distribution, okay? Wherever you see a summation, replace it with the integration, okay? So the take-home message from this very first lecture, first slide, is that whenever you see read some papers and you see a lot of integrations, don't be scared. They're essentially talking about some form of area under the curve most of the time. Okay? So we talk about the cumulative density function, or the CDF, which gives you the total area under the curve for a given range. And this range is going to be typically a subset of the range from, let's say, minus infinity to plus infinity. Okay? So hence, we talk about the cumulative density between the range A and B. So the probability density function is defined for some longer range. So the PDF is defined over some longer range, but now we can talk about the CDF within a restricted subset, A to B. Okay? So the important thing, again, to remember here is that a simple way we want to calculate the area between A and B, typically, is that we would compute the integration from minus infinity to B. So we'll calculate the area all the way from minus infinity to B. So we get this whole area. And then we subtract the area from minus infinity to A. Okay? So that way we get the area between whatever we're looking to find out. So that is the area between B and A. Okay? Okay, so a lot of these properties follows from our discrete distribution. So these are just the continuous analog of the discrete case. Okay? So obviously, if P of x is a probability density function, then the first statement has to be true for a univariate distribution. Okay? Is that clear? So we just have a single variable, and the maximum range possible is minus infinity to plus infinity. So hence, the total area under the curve has to equal to 1. Otherwise, it is not a PDF. And as I said earlier, we talk about the CDF between A and B as given by this definite integral from... Oh, yeah. So the second one is simple. So if you talk about the probability density at the cumulative density at any single point, that's always 0, right? Because the area for a point, regardless of how long it is always 0, right? Okay? And now we typically write this shorthand, f of a, as a shorthand for the definite integral from minus infinity to a. Okay? So as I said, explained earlier, we kind of sweep the area all the way from minus infinity up to a. Okay? And as a shorthand to that equation, if we replace a with x, we get this equation. Okay? So this simply means that f of x integral p of f dx, where the range is from minus infinity to x itself. Okay? So we call f of x as the CDF, or the cumulative distribution function, and clearly the PDF and CDF are related by this differential equation. Yeah? Because integration and differentiation are inverses of each other, so hence the two are related by this equation. Okay? Now, just to stress this point here, the point that f of x equal to a is 0. So if we look at this equation, it simply says that the meaning of the PDF simply means that if you take an infinitesimal, a very tiny area, right, for a given point, left and right, so delta by 2, let's say, then that small area is essentially equivalent to the PDF. Okay? And that is essentially what we know as the meaning of differentiation and integration. Is that clear? Okay? So now the corresponding equations for expectation and variance is given by these equations. And there's no surprise here. All I've done is replaced the summations with the integrations. Yeah? Now, before moving on to Bayes' theorem for continuous distributions, we should talk about the law of total probability. Okay? So again, the same thing. So this is also known as marginalization. So you can think of marginalization as variable elimination. Okay? So the point is that if you have a joint distribution, let's say you have a distribution which has x and y, but you want to average out the effect of y. You don't care about y. Then we can marginalize out y by using the law of total probability. Okay? So we then sum over all the values of y using this equation, and we can just simply compute the kind of the average value of p of x. Okay? So similarly now, moving to the continuous distribution, we simply replace the summation with the integration. Okay? So that gives you the law of total probability. It also gives you the variable elimination procedure. Okay? Also the marginalization method. Okay? So they all mean the same thing. So moving to Bayes, so obviously this equation is not a surprise anymore because all I've done is, for the discrete case, we have that summation in the denominator, and now we just replace the summation with the corresponding integration. Okay? Any questions? So good time to ask any questions, because now we'll come to the real distributions and things will get a little bit more complicated. Okay, so first, I spend a very short amount of time on the normal distribution. So the normal distribution is the most famous distribution, also known as a Gaussian distribution, invented by Gauss in the 1700s. So it's very old, okay? So it's one of the most studied, most well-known distributions, okay? And it gives you the familiar bell-shaped curve, okay? So why is normal distribution so important? Anybody would like to say?
Very common in nature.
Okay, very common in nature. Anything else? Can somebody give us an example of a normal distribution? Sorry? Okay, that's a good one. So distribution of height of people. So the most famous one, from my point of view, as a teacher, is the distribution of the marks of the students. Okay, so that follows a normal distribution as well. Okay, and so those universities which tries to use GPA or something like that. What they do is they take a normal distribution for a given class, given exam, and then they standardize that. Okay, so that way all the the distribution for all the different classes are the same. Okay, by scaling, for example, that distribution. So that's how you get the scaled marks. Okay, that compensate for exams being too easy or too difficult. Okay, so so the normal distribution is given by this equation. So it has got just two parameters. One is the mean, and the sigma is the standard deviation, or the sigma squared is the variance. Okay, so so the parameters mu and sigma squared are known as the mean and the variance. So the nice thing about this equation is that if you calculate the expectation of this distribution, or the mean of this distribution, it is equal to mu. If you calculate the variance of this distribution, it is equal to sigma squared. Okay. So so that is why this distribution is so elegant and nice. So the mean of this distribution is the point where the value of the PDF is the highest, okay? So what about the variance? What about the standard deviation? So what does the standard deviation control? Anyone? Sorry? Okay, anyone else?
Percentage of data concentrated within sigma.
Just in terms, just geometrically speaking, if I make sigma large, what will happen to this curve? Okay, very good. So that's the only thing you need to understand. If I increase sigma, this thing will become stretched, right? And the height will decrease because the area has to be equal to 1, remember? So you can't increase this without decreasing the height. Okay? Similarly, if you squish this, the height has to increase. Yeah? So that is the only thing you need to remember, what it controls. And the normal distribution has infinite range defined between minus infinity and plus infinity. Okay. Although typically, given any kind of a typical normal distribution, you would expect that the PDF of this of the Gaussian will approach very close to zero very quickly, obviously subject to the value of the standard deviation. So okay, so if you vary the mu, all you're going to do is shift the mean parameter. Okay, so that controls. So that is also known as the location. So that controls the location of that distribution. Okay, and when you vary the sigma, that controls the scale. Okay, so we typically talk about location and scale. Okay, which means the same thing again. Okay, so why is the normal distribution so important? It has to do also with the central limit theorem. Okay, so the central limit theorem says that if you take any distribution or any combination of distributions, it doesn't even matter that the different distributions come from the same distribution. Okay, arbitrary distributions. Now you calculate the distribution of their sum. So if you sum up the values of different distributions, as the number of components inside this sum increases, approaches infinity, so the number of things you're adding up approaches infinity, that distribution always converges to a Gaussian distribution, regardless of what the original distributions are. Okay? So this is a very celebrated theorem in statistics. So for example, the sum of the face value of randomly drawn playing cards has an approximately Gaussian distribution. Okay, so this is the sum. Okay, so typically the Gaussian distribution is the distribution of choice for many modeling problems. Okay, especially in the humanities, social sciences, and so on. This is a distribution of choice. Okay, so typically you would always try your Gaussian distribution, and if you're unhappy for some reason, then you move on to other distributions. Okay? So myself, being an unhappy person, I'm going to talk about now the beta distribution. Okay? So switching topics now, let's talk about the beta distribution. Okay? So to motivate the beta distribution, I would like to think about a kind of an artificial scenario. Okay, the scenario is that we have a factory that produces coins. Okay, so let's say you have a factory, and let's say you have a factory too. Okay, so you know he's trying to save a lot of money, so he's built a very cheap factory. So he produces coins. You also produce a lot of coins. You, being a very rich person, you know, you invested a lot in your factory. Okay? So I've sampled a coin from his factory. Pick a random coin. Okay? And I realized that the coin from his factory is not very balanced. Okay? I pick a coin from his factory. You know, I throw it, let's say, 100 times. In his case, I, let's say, get 49 heads and 51 tails. So pretty good. In his case, the first coin I picked, I got, you know, 30 heads and 70 tails. The next coin I picked, I got the opposite, you know, 70 heads and 30 tails, right? So his factory is producing, you know, random junk. Okay. This guy's factory is pretty good, okay? So what we have is that we have, if you're given any factory, let's say his factory or his factory, we have a distribution over the bias of the coins, okay? The question is, how do we specify some parameters that's going to say, okay, I can expect this kind of distribution of the coins from each of these different factories, okay? So there is a distribution over the bias of these coins, Now the question is how to model this distribution. Okay? So remember that the output from this distribution is a number between 0 and 1, which is the bias of the coin. Okay? Every time I sample a coin, I get a number. That number is between 0 to 1. Okay? So let me ask you this question. So he is a very rich man. He spent millions and millions in his factory. Is it possible that I pick a coin from his factory and the bias is exactly 0.5? Okay, any thoughts there? Any answers? Okay, let me repeat that question. So, you know that he's got a factory, yeah? And his factory produces coins. So we pick a coin from his factory, a random one, okay? So I am the factory inspector. So I go visit factories, check the quality, okay? So is it possible that when the coin I picked has a bias of exactly 0.5? How many for yes? Okay, not many, about 10. How many for no? So I say this to my class, you know, there's a class of 100, 10 people say yes, other 10 people say no. So there are 80 who haven't raised their hands. So what are those 80 people doing? They're sleeping. They're not paying attention. They didn't understand the question. They can't be bothered. Okay? So I'm not able to take a vote because the distribution was roughly the same. Okay, so those of you who said no, can one of you provide an answer to this question? So what is the reason? So who said no? Somewhere here. Someone said no here. Now nobody's raising their hand, see? Okay. Anybody would like to volunteer and say why it's a no? So just to understand this thought process, so it is a thought process, right? So let me just give you this idea, okay? So I pick a coin and I measure the bias. Let's say I have some sophisticated way of measuring this bias, which is not that easy to define either. It could be that the bias of this coin was 0.4999999, or it was 0.5000001. Okay? So the probability that is 0.5 is going to be quite low. Right? Okay? So because we are now in the continuous case, in fact, as I explained ago, the probability that it's exactly that is always going to be 0, right? So now the point is that there's always some distribution, right? So all we can expect from his factory is that this distribution is very sharp, right? As soon as you move away from 0.5, the distribution just tails off. In his case, the distribution is quite flat, or even straight, so that means he produces all kinds of coins because he doesn't care. Okay? Okay, to now move on to defining the beta distribution, firstly we need to define the gamma function. Okay? So the beta function, so the beta distribution is the analog of the binomial distribution to the continuous case. Okay? Remember that the binomial distribution is only defined for specific values for the natural, positive natural numbers, right? Or the non-negative natural numbers. So So what we want to do is that we need to generalize the binomial distribution to the continuous case. So first thing we need to do is that we need to define the analog of the factorial function, okay? Yeah, so remember that factorial 4 is 4 times 3 times 2 times 1, right? And factorial 3 is 3 times 2 times 1. Now I ask the question, what is factorial 3.5? And you say, well, that's a stupid question. Okay, but now let me provide an answer to that. Is that what if we want the factorial to be defined for all values? Because we know what factorial 4 is. That's a bigger number. And we know factorial 3 is a smaller number. So obviously 3.5 should be somewhere in between. So we want a function that can interpolate between all values of x where the factorial is not defined. And the values for x where factorial is defined, we want the function to give you exactly the same answer. Okay? So we want an interpolation function that expands the factorial function to the real domain. Okay? So the gamma function is defined like this. Factorial of n plus 1 is n factorial for natural number n. Factorial 1 is obviously, sorry, gamma 1 is factorial 0, it's defined as 1. And gamma half is same as factorial minus 1, as you say, because it's 1 minus. So that's why, and that comes out as a square root of pi. And gamma of 0 is factorial minus 1 is pi by 2. So the nice thing now is that this gamma function is defined for lots of cases where factorial is not defined. Okay? So the gamma function can be used to interpolate for values for which the factorial is undefined. Okay, so now here's the beta distribution. So you might say, why I'm putting this formula? It seems like a random formula. Okay? So, so another way to think about this equation is that I want a distribution which has got the same shape as the binomial distribution. Okay? So remember the binomial distribution. The binomial distribution is defined by n factorial divided by the total number of heads, total number of tails, factorials in the denominator, right? Theta to the power k, and 1 minus theta to the power n minus k. Okay? So you know the shape, okay? So got some constant, and it's got two things, okay? So those two things I want to be the same. I have theta and 1 minus theta, okay? And I have the parameters alpha and beta. So you can ignore the minus 1. The minus 1 is just a mathematical convenience. Just makes the equation a little bit easier. But even if you didn't have the minus 1, it wouldn't make any difference, okay? So now I have some constant in the denominator, okay? So this is known as the beta function in the denominator, okay? So there are two things here. One is the beta distribution, which is given by this equation, and the second is the beta function, which is given in the denominator, okay? So you can think of the beta function as giving you some constant value, okay? So the idea is that if I want to invent a new distribution, I think of some shape, and the shape is given here by this numerator, and I divide by some constant, okay? And then I figure out if that could be a probability distribution, okay? So we know that for this to be a probability distribution, the integration has to add up to 1. The area under the curve has to add up to 1. So if I can find a constant such that the area under the curve comes out as 1, then I have invented a new distribution. Okay? So that's the name of the game. So you can invent new distribution, you can choose arbitrary shapes, you can put some constants, you can do the integration, and if you're able to solve for the value of the constant, you're able to come up with a new distribution. Okay? So to go through this game now, to be able to show that this is a proper distribution, this integration has to equal to 1. Okay? So now we have decided that because the theta value is between 0 and 1, that is the bias of the coin, the range is between 0 to 1 only, right? So the integration now has to equal to 1, okay? So now, for this to be a proper distribution, just moving this beta over here, this integration has to equal to 1. Okay? Is that clear? So, how do you think we can solve this integration? So remember that when you do this integration, right, because this is a definite integral between 0 and 1, the result of this integration, the resulting equation from this integration, will it have a theta in it or not? So the formula you're going to get here, will it have theta in it or not? Okay, let me just see if you're sleeping or not. How many of you think there will be theta once this integration is solved? Anybody? How many think that there will not be any theta after? Okay, I have managed to wake more people. That's good. Okay, so we can solve this integration using integration by parts. I'm not going to go through this detail. It's not that important. You know, you can look it up and solve this. So I think the concept is more important. So you can do integration by parts, and you can solve this equation. Okay, by the way, this derivation is only, strictly speaking, is only true for positive natural values of alpha and beta. So it's not true in the general case, but you get the idea. So now, the key point is that we have solved this integration, and we get this result. Okay? Now, if you compare this to our binomial distribution, can you see the analog of this in the binomial distribution? So what is the corresponding part of the equation in the binomial distribution? What does this correspond to in the binomial distribution? Anyone? Sorry? Okay, let me just say, let me just repeat this, okay? So let's look at this one. Gamma, alpha plus beta. What does that correspond to in the binomial distribution? So that corresponds to n factorial, right? So this is just the inverse of the n choose k, right? So you have n factorial divided by h factorial, number of heads, times t factorial, number of tails, right? Or k factorial times n minus k factorial, right? N minus k is the number of tails. Yeah? Okay, so this is just the reverse of that, okay? Is that clear? So you see that now what you've derived is something very, very similar to the binomial distribution, except that this distribution is now a continuous distribution. Yeah? So now, if you substitute for alpha and beta equal to 1, what you recover is a uniform distribution. So now if you substitute for alpha, so now this is our beta distribution. So if you now substitute for alpha equal to 1 and beta equal to 1, all of this becomes 1, everything becomes 1. Okay? So that means you have a uniform distribution. So why is this a uniform distribution? Anyone? Let's see how many of you are awake. Sorry? Yeah, but remember the area has to equal to 1. It's not enough for the probability to be the same. Anyone else? Yeah, we're integrating from 0 to 1. So the width is 1, and the height is also 1. So it is a 1 by 1 square, right? So hence, it is a probable. So hence, the total area is 1. Okay? Okay. So now if we look at the beta distribution, this is what we're going to get. So let's start with the uniform distribution. So for the uniform distribution, alpha equal to beta equal to 1, and this is what we're going to get. Okay? And now let's say we take the green one, alpha equal to 5, and beta equal to 1. So we get this one. So I want to go back to the thought process I mentioned earlier. Okay? So let's refresh our memory. Okay? So I'm the factory inspector. Each one of you a coin, right? All of you have been sampled from the same factory, and I know the parameters of this factory, the alpha and beta value. Okay? And for each coin, I know the bias. I know the theta value. Okay? So what does the theta value tell us? If the theta is 0.5, it tells you that the probability of heads is 0.5, and the probability of tails is 1 minus 0.5, 0.5 again. Okay? If the theta is 0.6, it means the probability of heads is 0.6, and the probability of tail is 1 minus 0.6, so 0.4. Okay? Yeah? So I know the theta value for each one of you. I also know the alpha and beta value of the factory. So the factory is parameterized by the beta distribution, right? So for each one of you, I know the probability corresponding the probability that this coin was generated by this factory, okay? So I can calculate the beta value, the beta probability value for each coin, okay? So hence, a random coin will generate some number of heads, some number of tails, is going to be the average produced by all of your coins, right? Is that okay? So the average now is going to be first. So what is the process? First, I sample a coin from the factory. I got one of you, right? And now I throw the coin 100 times, let's say, and I calculate the number of heads and tails, okay? And the binomial distributions tells me what is the probability that I'm going to get 50 heads and 50 tails, let's say, right, from 100 throws. The binomial distribution will give you the value for all possibilities, right? Knowing the theta value, it'll tell you what is the probability of generating 10 heads, 90 tails, 20 heads, 80 tails, and so on. For each one, I know what the probability is, right? Okay? So the average is what I'm looking for, right? So that is the average value of the probability of a random coin sampled from a factory with a known value of alpha and beta, where the factory itself is parameterized by the beta distribution. Okay? Okay, so you need to understand the setting. The maths is easy. Everybody got that? Okay, so we are back to where we were before the tea break. Okay, so as I said, if you take a random sample, regardless of the size of the sample size, it is always going to be an approximation, right? So to calculate the exact value, we have to do the integration. So we now integrate for all possible values of theta given by the beta distribution, okay? So hence, we can use this equation. So the first equation is the beta distribution. It tells you the probability of the bias of the coin, the probability of any coin from this factory, okay? And the second one is from the binomial distribution. It tells you the probability of generating some number of heads and some number of tails, okay? And we integrate this out. So when you do this integration, in the resulting equation, is there going to be any thetas in the resulting equation? So when you do this integration, will you see any thetas afterwards? Yes or no? How many for yes? How many for no? Okay, half of you are still sleeping. Okay, so the whole point about integration is that when you do the integration, that theta is going to disappear. Why is that? Because for every value of theta, you're calculating the value of this equation. So you have substituted for all possible values of theta, right? So there was not going to be any theta because you're saying, okay, for this value of theta, what is the result? For another value of theta, what's the result? You're adding it up. So you're telling the equation, you're giving the equation all the possible values of theta, adding it up. So hence, the theta will disappear, right? Okay? So this is the same as I mentioned earlier, the law of total probability. So this is equivalent to what we call marginalizing out. So we marginalized out the variable theta, also known as integrating out. We have integrated out the theta, okay? So you would see in papers integrating out or marginalizing out. Means the same thing, that we have eliminated the theta value by substituting for all values of theta and averaging it, okay? So now, typically when you have integrations of this form on pen and paper, it won't be always possible to solve this equation, okay? So integration can be quite difficult depending on the shape of the things you're trying to integrate, okay? So if the shape of this equation and the shape of this equation is the same, then this equation can be solved, this integration can be solved a lot more easily, okay? So in that case, we're going to say that these two distributions are conjugate, okay? So that is the technical term. So we use the word conjugate. So it means the integration, the shape of the equations are similar, and that this integration can be solved on a piece of paper, okay? So we say that these two distributions are conjugate. And then you can look up Wikipedia, for example, and check which distributions are conjugate which other distributions. So it'll tell you, like, for example, the conjugate distribution for the binomial is the beta distribution. The conjugate for the Gaussian distribution typically would be something like what's known as the Wishart distribution, could also be the Gaussian distribution. So that we can solve this integration on a piece of paper. So the resulting equation is simple. So we can do the evaluation. So we can calculate it easily. Otherwise, you'll have to resort to a numerical approximation.
So my question is, why the binomial distribution is conjugate of beta distribution?
That's because, as I explained before the tea break, so that's a good question to refresh our memory. That's because if you look at the shape of this distribution, I've deliberately designed this distribution to look very similar to the binomial distribution, right? Because the binomial distribution also got theta to the power number of heads and 1 minus theta to the power number of tails. And this beta function here is very similar to n choose k, right? N factorial divided by h factorial times t factorial. Right? So that's why these two distributions have the same shape, and hence they are conjugate. Okay, any more questions? Okay, so now what I want you to do now, so this is not a reading exercise. I want you to actually solve this by yourself on a piece of paper. Okay, so here's the exercise. The exercise is very simple. Here, we're going to substitute the beta distribution, right? So this is a Lego exercise. So although the equations look very difficult, and they look very difficult, but if you are able to decompose it into the building blocks, most of these equations are very simple, okay? So it is like Lego blocks. So here, we have two Lego pieces. The first Lego piece is the beta distribution. The second Lego piece is the binomial distribution. We're putting them together and we're doing an integration. Okay? I have told you what the beta distribution is. I've told you what the binomial is. And you have got a cheat sheet which tells you what they are as well. Okay? So, what I want you to do now is for the beta distribution, I want you to plug in this equation. Okay? On a piece of paper. Okay, so you have that equation. So the equation I want you to write on a piece of paper is this equation. Okay? So we start with this equation. And you know the binomial distribution, right? So you can plug in the binomial distribution. Okay? And I tell you what C is. So C is C1 and C2. Okay? C1 heads and C2 tails. Or whatever you like. K heads and N minus K tails. Doesn't matter. Okay, so here's the first step. So I plugged in the beta distribution here, and I plugged in the binomial distribution over here, right? Here, C1 is the number of heads, and C2 is the number of tails, okay? Okay, so all of you can write that equation, and now try to solve it, okay? So it's much more easier if you try to solve it than trying to read my slides. Reading my slides is hard. Doing it yourself is going to be easier. What I want now is a volunteer who's going to come and explain this slide so I can have a rest.
So we can just suppose C1 plus alpha to be M and C2 plus alpha to be N. So we have a beta with the function with the parameter M and N.
Yeah, that's correct. And that's exactly what you get. Anybody would like to come and volunteer? So another point to note about the Lego brick analogy is that a lot of the maths we do in machine learning, and especially Bayesian machine learning, follows this kind of approach, right? So the idea is that when we are defining a machine learning model, what we're trying to do is that we're trying to figure out what the different Lego blocks are going to be, okay? And once you know what the building blocks are, then you can assemble it. Okay, and some of it you can solve on paper. Some of it you will need to use some sort of numerical method, but the principle remains the same. Okay. So I had a question just now. How do you go from this top to the next line? Okay, that line, top line, is just the definition of conditional probability. Okay, right? Anybody who hasn't understood, raise your hand. Okay, that is just the definition of conditional probability. Okay, so that is simply Okay, that is just that. Okay, so actually I might want to expand on this a little bit if some of you, I might have skipped a couple of steps. This is also to do with some of the independence assumptions that Samrachana mentioned earlier. So let me try to do this. So we have so firstly, we are happy with the first step, right? Okay, so which equation is this? This is the law of total probability, right? Okay, so now we can split this out into by using the definition of conditional probability. Okay, so here I'm assuming, if you just assume that this alpha beta always remains on the right-hand side, okay, I just copy it, okay? So that doesn't change. So remember that from the definition of P, C, theta, okay, you're happy with this? Everybody's happy with that, right? So here, all I've done is added the alpha beta conditionals. Okay? Okay? Is everybody happy with that? Okay, so hence, I can get this equation. Is that clear? So now, the point is this. I'm in the factory. I know the alpha and beta values of the factory. I sampled a coin, okay? And I know the theta value of that coin, okay? Once I know the theta value of that coin, the fact that it came from your factory or your factory becomes irrelevant, okay? Because I know the property of that coin once I know the theta value. Hence, the probability of C given theta yeah, is independent of alpha and beta. Okay? So hence, this thing can be written as PC theta. Because once you know the theta, the fact that it came from some factory is irrelevant because you already know the theta. Okay? Is that clear? So we can use the notion of independence to get rid of the alpha and beta there. Yep, we have a volunteer. Okay, round of applause. One second. Yep.
So now that we have this derivation P of C given theta, and from here we are basically substituting the functions for the binomial and the beta prior. Once we have that, since the integration is over d theta here, we can take out any term which does not have a theta outside of the integral. So that would be all terms with n, c, and your b of alpha comma beta. So let me rewrite the beta as b of alpha comma beta and theta of alpha minus 1 and 1 minus theta to the b minus 1. So this was our beta distribution, and this b is what is written as this function extension. So once we have this, we are basically multiplying theta to the c1 and theta to the alpha minus 1 to get a to the m plus a to n times a to the n is a to the m plus n. And once we have this, so you can basically see that from the definition of a beta distribution, we have that this has to integrate to equal 1, which means that your b of alpha comma beta is nothing but integral of theta to the alpha minus 1 times 1 minus theta to the beta minus 1. Right? So if you have any function of theta to something times 1 minus theta to something, you can write it as a b of alpha comma beta. And we have exactly that in this side. Theta to some term and 1 minus theta to some other term. So you basically have to find out what this alpha and beta are. So that would be equal to C1 plus alpha and C2 plus beta, because here if you substitute C1 plus alpha, this becomes B of C1 plus alpha, comma C2 plus beta, which would be equal to theta to the C1 plus alpha minus 1 and C2 plus B2 minus 1. And we know that B of alpha comma beta expands to this term. This is 1 over B of alpha comma beta. So now that we know that this term is equal to B of, let me write that, B of C1 plus alpha, comma C2 plus beta. So since B of alpha comma beta is equal to this, so 1 over this, so then find out what B of C1 plus alpha, comma C2 plus beta is, which would be gamma of C1 plus alpha, gamma of C2 plus beta, excuse my handwriting, sorry, gamma of C1 plus C2 plus alpha plus beta, and you have your solution.
Okay, thank you. Okay, so I guess you have understood from this derivation the point about conjugate distributions, okay? So if these distributions were not conjugate, it might have been difficult to do this integration analytically. So when we say analytically, typically we mean on a piece of paper, okay? So we can get the closed form solution. Okay, so moving on. So this distribution is known as the beta binomial distribution. It is actually quite an important distribution used primarily for unsupervised learning, so for clustering algorithms. So we're not going into the details here. But the key point here is that, so what we have just derived is the beta binomial distribution that gives the averaged probability of drawing C1 heads, C2 tails from a coin that has been sampled from a beta distribution from a factory with parameters alpha and beta, okay? So I just want to go back to this equation once more and make sure you understood this. So I want to go back to the analogy I gave earlier. So what is happening here in this integration is that we go to the factory, we pick a coin, we got a coin, okay? We now know the probability from the beta distribution of this coin. Now for the C1 heads and C2 tails, we know the probability of generating C1 heads and C2 tails using the binomial distribution. Now we go to the next coin and carry this on. So this integration is simulating that process, in an infinite scale. Okay? And we can compute this, work this out on a piece of paper exactly. Right? So no infinite for loops needed. Just a piece of paper. All right? Okay, so So here, the key point is that the theta parameter has been integrated out or marginalized out or averaged out, and hence no longer appears in this distribution. Okay? So it tells you, so what does it tell you? If I just know your factory, I don't even need to know the binomial distribution. I can tell you a random coin picked from this factory, what is the probability of generating some number of heads and some number of tails directly, right? By averaging over all possible coins that his factory produces. Okay? Okay, so now we will move on to inference. So typically in machine learning, we're interested in learning some parameters, okay?